For the session, we're going to talk about the AI-based computer vision approach that Algolux is developing and deploying to deliver very high robustness of computer vision in all conditions, for all conditions. And what we mean by robustness is being able to provide accurate computer vision in harsh scenarios, and those would be low light, bad weather, things of that nature. And we'll give a little bit of insight and examples of the work that we're doing here and some benchmark information that we've been able to significantly outperform state-of-the-art solutions today. So from a mission, I'll give a little bit more about Algolux toward the end as well. It is really all about robust perception. And while Algolux's technology can be applied to really any application, we do quite a lot in the automotive ADAS and autonomous vehicle space, as well as video security, areas that really have a need for safety and reliability and accuracy. And so robustness is really a very important aspect for any vision system, but especially in those cases where lives that are at stake in some fashion. And so a little bit more about Algolux. We provide really two product lines. I'll be focusing more on our Eos embedded perception software, and that provides the extremely high robustness and accuracy versus state-of-the-art networks today. We'll give a little bit more insight into that. And it's something that gets integrated into typically an embedded system. So a camera at the edge or a central compute node in an automobile or a AV. But we also have another product line called Atlas, which is applied to optimizing cameras for computer vision. So essentially a camera today outputs an image that then goes into a computer vision model, and very expert imaging teams tweak the parameters on that camera's image signal processor to get the best image out of that camera. But that best visual image may not be the best one for computer vision. So you can apply Atlas to a camera to immediately improve computer vision results. Whereas with EOS, if you want to get massively improved results, then you would integrate EOS into that system. So that's just a little bit about the technology that we provide to the market today. But let's dive a little bit more into what we do for providing robust perception. And as I mentioned earlier, this is fundamental. There's a lot of excellent research and work that's been done, especially over the last, say, 8 or so years in applying deep learning towards the computer vision task for object detection, free space, for fusion, things of that nature. But fundamentally for the applications that are being tagged for computer vision, robustness is critical. And if we look at what are some of the challenging factors for why systems are not robust today, let's take a step back and look at what is a typical vision system at an abstract view. So a typical pipeline that's doing computer vision, you have your camera, which consists of the lens, the sensor, which converts the photons into electrical signals. And that is then converted by the ISP through a pipeline of image processing stages, such as denoising, sharpening, color correction, things of that nature, to then output an image that is pleasing to a human eye. Then, and as I mentioned before, the ISP is highly parameterized with many registers that the imaging team can set to determine the characteristic or the character of that image. So is it oversaturated for certain markets? Is it sharp, overly sharpened and things of that nature? And then that's then sent into your perception model, doing, say, for example, object detection in this example here. And these systems work quite well in good conditions, such as good lighting and weather conditions. but they really fail pretty quickly and poorly under harsh conditions, like this image here, where you're in the darkness, there's quite a bit of glare, it's hard to resolve due to the contrast issues, the other objects out there from this image, and it basically, this particular detector missed about 4 objects that it should have detected. We take a very different approach from this. We actually apply an end-to-end learning approach that bypasses the traditional hardware ISP that you'll find in a normal processor or SoC being used in these vision systems. And we take the raw sensor data directly into the network. And so we're starting with essentially that ground truth unprocessed data from that sensor into the network. And then we do a couple interesting things there. First, we do a characterization or calibration of the lens and sensor to essentially get lens characteristics and sensor characteristics, such as the noise model, black levels, things of that nature. And we apply those as priors into the network for the training. While at the same time, we also apply that same characterization information, this image formation model that we build from that characterization, to then adapt the training data set to be as if it was taken, the training data set was taken by that actual camera. And so very quickly, we can adapt the EOS model through end-to-end training with the data that is simulating as if that whole data set was captured by the actual camera that's going to be deployed, while at the same time the end-to-end training allows the early layers to learn the best way to process that input sensor data, that raw sensor data, specifically for the later layers that are, say, doing detection or some other vision task. And that allows us to compensate for these harsh conditions that result in low contrast or high noise. The other interesting aspect about that training process is that when we adapt that training data set for that particular lens and sensor, we can also synthesize a much larger data set that covers the operational corners of that sensor. So we can basically expand that data set to cover very high illumination to low illumination scenes, high noise to low noise, high contrast to low contrast, and create a much more extensive data set from that for that training process. And so this is very different than what's done today, which is the team tunes the ISP, and then they typically will use an ensemble of data sets to train the perception module. Very, very rarely do you actually build a training data set with the actual camera that you're trying to deploy, because you're trying to capture hundreds of thousands of images. So it's very expensive from a capture and annotation and curation standpoint of that data set. So this allows us not only to provide this approach not only provides very significant robustness and accuracy advantages, but it also allows easy scalability if the camera changes. So we can quickly tailor the network to any camera configuration, from a narrow field of view to wide field of view to a regular RGB sensor that we're all used to taking pictures with, to, say, an automotive sensor that is only using a red, clear, and clear color filter array. So that allows us a lot of flexibility and scalability for these various applications. So hopefully that gives kind of a quick insight into that, and we're more than happy to answer some questions on that. But I wanted to show some results of what EOS can do. And here's 4 examples in various harsh conditions: low light, snow, fog, and dirty windshield and glare scenarios. You'll notice, like in the foggy night, very noisy image here. You'll notice that there's a lot of objects. There's a lot of occluded objects. Typically trained networks fail pretty horribly on these scenarios. And then the other thing to note is that bottom left stream or example that we're showing, it's actually a much wider field of view lens. It's a 120 degree field of view lens versus the 40, and a different sensor color filter array. This is in our CCB, so red, clear, blue. color filter array, different than the RGB ones here. And we were able to tailor this network approach, our EOS network approach, to that camera without any retraining or redata capture. So easily scale and support this very different camera configuration. In the normal world, you would, or in the traditional way, we'll call it, you would have to recapture the data set with that new lens and sensor combination to then begin properly training that data set for this much different camera. Here's an interesting example where we're comparing against Tesla's object detector. We actually recently cracked a late model Tesla, and we're able to access the sensor stream. So we fed that into that was fed into the Tesla. We looked at the output, and then we fed that into the Algolux EOS approach. One thing to note is that Tesla actually does sensor fusion with image or camera and radar, and they're also doing tracking. We're actually comparing our results of just doing frame-by-frame camera-only detection versus the Tesla's fusion and tracking detection. So, in this last scene here, we're actually seeing significantly more vehicles and objects than the Tesla is able to resolve. So that's just an insight into these difficult scenarios, such as dark evening here, and small objects that we significantly outperform a commercial solution, we'll call it. We're not only focused on just simple detection with standard lensing. Here's an example of a fisheye pedestrian detection application. I don't have a video for this, just a still clip, just to show yet another application. Here's a kind of quick clip where we're doing lane detection, and we're comparing against the NVIDIA DriveWorks platform here. Again, it's a difficult evening scene, so difficult to resolve all of the objects here in the traditional fashion due to the low contrast scenes, where we're quite significantly outperforming both from a stability and tracking of lane standpoint as well as accuracy of tracking. And then here's an interesting one where we're showing some examples of doing free space detection versus another against the NVIDIA platform here as well. NVIDIA seems to like to climb on top of the car in front of it there. But just another example beyond just object detection, here's a semantic segmentation and free space detection application. And then we're doing some interesting stuff with depth estimation, whether it's stereo camera or actually fusion. Here's just a still from some of the work that we've been doing there to do learned depth estimation. So all of these applications are really applying a very interesting, novel approaches of machine learning or deep learning for these particular vision tasks. In addition, we do target embedded platforms, so we have to be quite efficient for that. And we have quite an efficient architecture. A very common comparison that we run up against is people like to know how we do against YOLO V3 from a performance standpoint, but we also significantly outperform YOLO by quite a large margin from a performance standpoint. And then here's just some metrics. We did an apples to apples comparison in harsh conditions as well as good conditions of 3 academic or open networks out there, the YOLO V3, the RetinaNet, and the MobileNet, where we're not only just outperforming these networks under harsh conditions, but really by a factor of 2 to 3x from a mean average precision standpoint. So very significant improvement in robustness and accuracy under harsh conditions. And in good conditions, we're still significantly outperforming them. And in this case, the networks were equivalently trained on these open COCO and Pascal and BDD 100K networks. On the prior example, we equivalently trained the network on the harsh data set. And then just a quick view that we are working on quite a bit of the perception stack, whether it's 2 to 3D detection, fusion, tracking, moving towards localization and further up the chain. So quite a lot of tasks that Algolux needs very brilliant help with. So hopefully there may be an interest in working with us on that. And then looking ahead, this is some interesting information that we have on our website. Most recently, the CVPR conference was last month. We had 6 papers that were accepted, and a number of them were oral presentations as well, which is a pretty small percentage of the overall presentations are oral, or papers are oral. And so we're doing very interesting work with replacing LiDAR with low-cost cameras using gated camera, or depth sensing as well, stereo depth sensing. Doing some exciting breakthrough work in sensor fusion to address things like asymmetrical distortions or asymmetrical failure, for sensor fusion. And for those two, as well as being able to do non-light of sight sensing, both with radar and imaging, so we can essentially look around corners. We've done some really interesting work with Daimler on that. And then a recent breakthrough on applying evolutionary techniques for optimization of the cameras that I mentioned before with Atlas. So we continue to actually do quite a bit of cutting edge research to help fuel the innovation breakthroughs that we're doing from a technology standpoint. And then kind of to kind of close out a little bit about Algolux. We're headquartered in Montreal, and we do have offices in Palo Alto and Munich. We've aggregated quite a global team of machine learning and computer vision experts in our Montreal office. So the R&D center for us is in Montreal. And the cutting edge research is led by our CTO, Dr. Felix Heide, who, in addition to his background in these topics, is working very closely with local universities in the Montreal area, as well as beyond. And from an industry standpoint, we've been recognized quite broadly across many forums for our AI and CB breakthroughs.